We've been looking at time domain responses of LTI systems. We're now going to take a look at what's called the frequency response of LTI systems. What this means essentially is that we're going to consider responses to inputs that are sinusoids. And in a sense, we're going to focus really on two-sided sinusoids, although in practice we can just use one-sided sinusoids and look only at the steady state component of the response, ignoring transients. This essentially will give us a different domain in which to look at systems. For instance, when designing control systems, control engineers tend to write specifications or requirements in the time domain. And those specifications, you've had a bit of a glimpse at them in the little problems on design of cruise controls. But sometimes the design is carried out on the S-plane. For instance, we talked a little bit about shifting poles around on the S-plane, and I hope that you saw the way using feedback to control a system can effectively shift its poles to different positions on the S-plane. We also do design using the frequency response, and this is often called frequency domain design, although the S-plane itself can be thought of as a kind of frequency domain. So sometimes we will translate problems from the time domain to the S-plane in order to solve them. Sometimes we'll translate them to this frequency domain that we're going to talk about now. And having these different domains and different ways to, and knowing how to move from one to the other, transform a problem from one to the other, gives us different ways of looking at systems and powerful ways of designing systems. So let's talk about what we mean by the frequency response of an LTI system. This is really a special case of the eigenfunction property that we saw earlier. If we have an LTI system, and we feed into it an exponential input, we saw that the response that we get is h of s times e to the st. And here I'm talking about two-sided exponentials. And this h of s is simply the transfer function of our LTI system. Now, we can't necessarily generate in the lab all the complex exponentials e to the st that we might choose to, but we can consider the special case where j is imaginary, where s is imaginary, so where s has the form j omega. In that case, we're feeding in the input e to the j omega t, which is essentially a sinusoid. It's cosine omega t plus j sine omega t by the Euler identity. And by this eigenfunction property, what we get out as a response is the same sinusoid, except it is multiplied by the quantity h of j omega. Now, for that reason, this quantity h of j omega we call the frequency response. Why do we call it the frequency response? Well, if you look at this, it simply characterizes completely the response to an exponential, to a sinusoidal input. So for any angular frequency omega of that sinusoid, what you get as a response is the same sinusoid that you fed in, multiplied by h of j omega. But maybe it's not yet clear exactly what this sinusoid looks like. So let's take a closer look at h of j omega e to the j omega t. Now, since we're multiplying h of j omega by e to the j omega t, it's convenient to put h of j omega into what is sometimes called a polar form. So let's think of h of j omega as the modulus of h of j omega times e to the j times the angle of h of j omega. Okay? Just so that everyone understands what we're doing here, for a given value of omega, h of j omega is some point on the complex plane. Okay? So we could characterize it in terms of its imaginary, real and imaginary parts. Here's the real part of h of j omega, and here's its imaginary part. And that's a representation that's convenient if we're doing addition or subtraction with h of j omega, because then we simply add or subtract the real and imaginary parts of our two complex quantities. When we're doing multiplication, it can be much more convenient to write h of j omega in this form in terms of its modulus and its angle. Now graphically, its modulus is just the distance from the origin to the point h of j omega on the complex plane. And its angle is this angle here, the angle of h of j omega. So note that if we take the modulus of h of j omega and we multiply it by e to the power j times the angle of h of j omega, then by applying again the Euler identity, we can rewrite e to the power of the angle of h of j omega as the cosine of the angle of h of j omega plus j times the sine of the angle of h of j omega. But if we multiply the modulus of h of j omega by the cosine of its angle, we'll just get the real part of h of j omega. And if we multiply the modulus of h of j omega by the sine of its angle, we'll get the imaginary part. So this simply gives us the real part of h of j omega plus j times the imaginary part of h of j omega. And that, of course, is just h of j omega itself. Okay. So we can express h of j omega as its modulus times e to the power of j times its angle. So if we go back to the expression for our output, we feed in e to the j omega t to our LTI system. What we get at the output is h of j omega times e to the j omega t. We're now in a better position to see what this output looks like. It's going to be the modulus of h of j omega times e to the power of j times the angle of h of j omega times e to the j omega t. So we get the modulus of h of j omega times the product of these two exponentials, but of course when we multiply these exponentials, we can add their exponents. So we get e to the power j times omega t plus the angle of h of j omega. So again, h was just our transfer function. So all we're doing to get this so-called frequency response is evaluating that transfer function at the point j omega on the imaginary axis. And that explains what happens to the sinusoid e to the j omega t when we pass it through our LTI system, if you like. In particular, we see here that the amplitude of our sinusoid gets multiplied by the modulus of h of j omega. And what the angle of h of j omega does is to shift the phase of our sinusoid. Okay. So you could, from this basic result, you could calculate what happens if our sinusoid is actually, say, sine omega t. In that case, the output will be the sinusoid, sine omega t, multiplied by the modulus of h of j omega, and with a phase shift equal to the angle of h of j omega. And you can see that easily by just expressing this sine omega t as e to the j omega t minus e to the minus j omega t over 2, and applying the result that we just saw using the principle of superposition. That shows you if you feed in the input sine omega t, what you get at the output is this same sinusoid sine omega t at the same frequency, but its amplitude is multiplied by the modulus of h of j omega, and its phase is shifted by the angle of h of j omega. So it's very easy to characterize the response of an LTI system to a two-sided sinusoid like this. It's important that the output is at the same frequency. If you feed a sinusoid into a nonlinear system, in general you will get a component of the output that is, say, a sinusoid at the same frequency omega t, but you will generally also generate harmonics. You will get other sinusoids at multiples of the frequency omega. With an LTI system, you just get a single sinusoid at the same frequency, but its amplitude and its phase are changed in this very simple way that just depends on the value of the transfer function at s equals j omega. So that again is why h of j omega is called the frequency response. Okay, so far I've been thinking about we've been talking about a two-sided exponential. In reality, in the lab, you obviously can only feed in an approximation of a one-sided exponential. So you'll find the same result essentially if, as long as the transfer function h of s is stable, and you wait for any transients to die down. So if you use the input sine omega t, say, times the unit step, the response y of t will tend to the modulus of h of j omega times the sine of omega t plus the angle of h of j omega as t goes to infinity. And in fact, when you have a stable system, you can draw the frequency response experimentally by going into the lab, feeding in sinusoids of different frequencies, and tracing these two quantities the modulus of h of j omega, and the angle of h of j omega, essentially as a function of frequency. We'll see that in fact we trace this in a particular way. We want it to be easy, just as in the case of the response in the time domain. We'd like to be able to draw the response in the frequency domain in a simple way by decomposing the plots for complex transfer functions into the plots for simple transfer functions. And in order to be able to do that, what we draw are Bode plots. We draw plots of the amplitude and phase in a particular form, which we call Bode plots. So this is just a graphical representation of the frequency response, which again consists of these two parts, the modulus and the angle, or the amplitude and phase, we sometimes say. And it has a special form that makes it easy to draw the Bode plot for a complicated transfer function in terms of the Bode plots for simple transfer functions. In particular, we plot the modulus h of j omega in decibels, versus the log to the base 10 of omega, the angular frequency. That's one plot. You need two plots because we have to represent both the modulus and the angle. So we also plot the angle of h of j omega versus the log to the base 10 of omega. And these are respectively called the magnitude and phase curves. And this has two advantages. First of all, it allows the curves to be sketched easily. And I don't know how much curve sketching you did when you were taking courses in calculus and that sort of thing, but when you're sketching curves, you often start out by drawing asymptotes, and that's what we will do in order to sketch these Bode plots. By drawing asymptotes, we'll be able to allow the curves to be approximated in piecewise linear form, so with straight line segments. And secondly, this approach will allow plots for complex transfer functions to be obtained simply by summing the respective components of the Bode plot for simpler factors. So instead of doing partial fractions decomposition, when we're working with frequency response plots, we will just factor our transfer functions. Draw the Bode plots for simple factors, and then we'll be able to sum the respective curves, the magnitude curves and the phase curves, to get the Bode plot for a complicated transfer function. It's relatively easy to see why that works with the phase curve. So suppose h of j omega is the product of the frequency responses corresponding to two simpler transfer functions, h1 of s and h2 of s. Well, then we know we can write h1 and h2 in this sort of polar form. So the product h of j omega has as its modulus the product of the moduli of h1 and h2, and it has as its angle the sum of the angles of h1 and h2. In fact, this is why this polar representation is convenient when you're multiplying or dividing complex numbers. You just have to multiply the products, multiply the moduli rather, and add the angles. So we see right away that the angles are additive, if you like. So if we can draw the phase curves for the simple transfer functions h1 of s and h2 of s, we just need to add them to get the phase curve for the more complicated transfer function h of s, because of the way these angles simply add. But we'll be expressing the moduli in decibels, and that's essentially a log scale, and that means that we get this additivity for the moduli as well. So both the angles and the moduli or amplitude curves will in fact be additive. So as we'll see later on, we'll be able to draw the Bode plots for complicated transfer functions by drawing the Bode plots for factors of those transfer functions and then just adding. But let's explain this logarithmic representation that we use for the moduli. As I said, we're going to express the moduli in decibels. And as the name suggests, a decibel is 1/10 of a bell. These bells are named after Alexander Graham Bell. And a bell is in fact the base 10 logarithm of the power of two signals. So a bell is a ratio, really. So the power, what do we mean by the power in a signal? The power is typically proportional to the square of a signal. Why do I say that? That's probably not obvious. Let's take a very simple example. Suppose we've got a simple circuit, the simplest possible circuit if you like, just consists of a resistor R. And we apply a voltage V across the terminals of this resistor. That gives rise to a current I. The relationship between V and I is of course given by Ohm's law. So V equals IR. But the power dissipated by the resistor is the product of the voltage and the current. V times I. Now, if we wish, we can use Ohm's law to express this power in terms of just V or in terms of just I. So I is just V over R, so we could write it as V squared over R. Or alternatively, we could write V as IR, in which case we get I squared R. In either case, the power is proportional either to the square of the voltage or to the square of the current. So we think of the power in a signal as being proportional to the square of that signal. So in bells, the ratio of the power of two signals F1 and F2 is, by definition, the log to the base 10 of F1 squared over F2 squared. See? And this, of course, is the same thing as the log to the base 10 of the ratio F1 over F2 all squared, which is the same thing as 2 log to the base 10 of the ratio of F1 and F2. So this is a way of writing the ratio of the power of these two signals in bells. But it's more common to use decibels, just I suppose because of the range, the numerical range that you get. And if you're using decibels, decibels being only tenths of bells, what you get instead is 10 log 10 F1 squared over F2 squared, dB for decibels, or 20 log to the base 10 F1 over F2. And again, that's decibels. Now, we know, okay, we just saw that the ratio of the amplitude of input and output sinusoids of an LTI system with transfer function h of s is h of j omega, or the modulus rather of h of j omega. So if we write this in decibels, since this is the ratio of the amplitudes, we need a factor of 2, and then we also have a factor of 10 because we're writing in decibels, so we get 20 log to the base 10 of the modulus of h of j omega. So this is actually what we'll plot as a function of the log of omega. Okay. So that is the magnitude curve that we're going to plot. As I said, the motivation, part of the motivation for this is additivity. So we know that the angle, if h of s equals h1 of s times h2 of s, we know that we add the angles of h1 of j omega and h2 of j omega to get the angle of h of j omega. But if we're expressing the modulus of h of j omega in decibels, that is, we're taking its log to the base 10 and multiplying by 20, well, that's just going to be 20 log base 10 of the modulus of h1 of j omega plus 20 log to the base 10 of h2 of j omega. So again, if we can break our transfer function up into simple factors, draw the magnitude curve or the amplitude curve for each factor, then we can simply add them to get the magnitude curve for our more complex transfer function. So that's one of the main reasons why we express the modulus in decibels. So it's probably time that we looked at some simple examples. Let's just start with some very simple ones, just to make these basic ideas a bit clearer. It's probably a good idea to start with an integrator. So as you know, if you feed into an integrator a sinusoid, the output's going to be sinusoidal as well. So let's take a look at the frequency response, which characterizes the amplitudes, the ratio of the amplitudes and the phase shift that this sinusoid goes through. Well, we know that what happens to the sinusoid as it passes through the integrator is completely determined by the frequency response, h of j omega. And in this case of the integrator, that's 1 over j omega. Okay. So again, the Bode plot that we're going to draw consists of two plots, one for the magnitude and one for the phase. What does the magnitude plot look like? Well, if we're plotting 20 log 10, the modulus of h of j omega, which is the magnitude in decibels, then that's 20 log 1 over omega, or minus 20 log omega. We're talking here about omega greater than 0. That way we can take the logarithm. So we're talking only about positive values of omega. Now, I've explained why we plot in decibels so that we get this kind of additivity property. But from this example, we see that expressing the modulus of h of j omega in decibels gives us a function of the log of omega. So in fact, we're going to plot the magnitude in decibels, this 20 log the modulus of h of j omega, as a function of the log of omega. And in cases like this simple one, we will get straight line plots, because this, in fact, is just a straight line on a plot versus log omega with a slope of minus 20. And we'll talk about the units of that slope in a moment. So if we plot the modulus of h of j omega in decibels versus the log of omega, we get a straight line. And here's a question. Where does the modulus become 0 decibels? The modulus again is 20 log 1 over omega, if you like. That's going to become 0 when 1 over omega is 1. In other words, when omega equals 1. So this intercept is going to occur when omega equals 1. In other words, when the log of omega equals 0. Let's write it that way. And this slope is going to be minus 20, but what does that minus 20 mean? Well, that means that the modulus decreases by 20 decibels every time the log of omega decreases by 1, or rather increases by 1. What does it mean for the log of omega to increase by 1? The log of omega increases by 1 whenever omega increases by a factor of 10. So we call that interval over which omega increases by a factor of 10 a decade. So we say that this slope is minus 20 decibels per decade. And that completely characterizes this magnitude curve. That gives us a plot of the modulus of h of j omega, but it's in decibels and it's as a function of the log of omega. And because we plotted it that way, it's a very simple straight line. Again, the intersect occurs when omega equals 1. And on a log scale, if we plot the actual values of omega on this log omega scale, it'll look something like this. So each of these intervals is one where omega increases by a factor of 10. So each of these is what we call a decade. So here, for instance, if we're a decade lower than the frequency at which that intercept occurs, this will have to be, the modulus will have to be 20 decibels. And 2 decades lower, it will be 40 decibels, because again, the slope is minus 20 decibels per decade. And that's how we're going to plot the moduli of these frequency responses. But that's only one half of the Bode plot. The Bode plot consists of 2 curves, one for the magnitude or amplitude and one for the phase. So now let's see what that other part of the Bode plot looks like. I always find that it's easy to visualize what happens to the angle of h of j omega if you draw a little plot on the s-plane. So for our example, h of j omega, again, is 1 over j omega. So we're interested in the angle now of this quantity. Well, when you divide complex quantities, like you divide 1 by j omega, what happens to the angles of those two quantities? You subtract them, as we saw by putting quantities into their polar form. So the angle of h of j omega will be the angle of 1, which is just 0, minus the angle of j omega. So the angle that we're looking for is actually the negative of the angle of j omega. Well, what does the angle of j omega look like as omega varies from 0 to infinity? Because we're only dealing with positive values of omega because we're taking logarithms. Well, j omega, if we plot it on the complex plane, it's always going to be on the upper part of the imaginary axis if omega is greater than 0. So its modulus obviously is omega. We took account of that when we were looking at the modulus of h of j omega. And its angle is right here. We see that its angle is always 90 degrees. So the angle of j omega is always 90 degrees for positive omega. We're interested in the negative of that angle. So our phase plot for this simple example of the integrator is going to be a very simple one. It's just a horizontal line. The phase, the angle of h of j omega, will always be minus 90 degrees. And we normally do use degrees rather than, say, radians when we're drawing these plots. So suppose this is minus 90 degrees, this is 0 degrees. Our phase plot for this simple example is just a horizontal line, like this. So together these two plots, which in this simple case are just straight lines, these constitute the Bode plot. And there's a more neatly drawn version in the lecture notes, which draws both the magnitude and phase curve on a bit of so-called semi-log graph paper. So you can see that Bode plot nicely drawn in the lecture notes. Well, there, we've said what frequency response is. It's this magical quantity h of j omega that completely characterizes the response of an LTI system to sinusoids. And we've seen how we're going to plot it graphically in the form of a Bode plot. And I can't stress enough that the Bode plot consists of these two curves. Despite it's being called a plot, it consists of two separate curves, the magnitude curve and the phase curve. So in the simple example of an integrator, this is what the magnitude curve looks like, a straight line with a slope of minus 20 decibels per decade, and an intersection when the log of omega equals 0, an intersect rather. And the second curve is this phase plot, which for our integrator is simply a horizontal line at minus 90 degrees. So we've defined frequency response and we've seen the simple examples. We'll go on to some more simple examples in the next lectures. See you then.